Hey y'all, let me go to relativity. Let me go over some of the problems. Don't forget to, I know I jumped chapter 4, but chapter 4 looks like chapter 3, and we are focusing on one slit only, and we did that in the lab. I think you guys are fine. So I'm trying to focus here on relativity. Um, I met Mark, and Mark said relativity is too boring, so that put me in big depression. So I think I should just apply for retirement because um, this subject is phenomenal. If you just stop thinking, the way our brain is set is in the classical terms, and when we learn relativity and quantum mechanics and all these aspects of modern physics, it should it should get crazy. And now Mark looked at me and said, "Oh, it's too boring. I'm not doing a good job here." So also I sent an announcement, and so Lorentz transformation I cover, but I'm not focusing on it. Yeah, we have some commotion here in the class in the house because of the prom thing. So don't I hope you don't mind the background. So let's go through. Make sure you review these conceptual questions, and let's go to the problems. Problem number two. Oh, let me get my my sheet. There you go. Problem number 23. Oh, wait a second. I have to enable Mark.
Are you dressed?
There you go. So number 23, this is simple. Yeah, we just apply equations. Come on. Number 23, 24 is the same silly thing. Number 25. So we have particles meson pi are produced by an accelerator if these particles travel. Now, in relativity, this chapter, what you need to know, you need to remember what is the definition of proper time. Proper time is a time that is measured by somebody that is at rest with respect to the object that the time is being measured. So you have to remember that. And you also have to remember the definition of proper length. Proper length is a length measure by an observer that is at rest with respect to the 2 points where this length is being measured. So sometimes you're going to see proper time and proper length in different rest frames. So be careful there. Okay. So be careful there. So again, proper length is a length that you go to point A, point B with a ruler and you measure, right? And proper time is a time that you are there in the lab and you see some event happening, and then you measure how long that event happened. Okay, so let's go to 25. So you have this particle produced by an accelerator, and these particles travel at a speed. The speed is always going to be the same. It's supposed to be the speed or the velocity relative to inertial frames is seen as the same regardless if you are in one or another rest frame. So it's assumed to be the same. The speed is the same. So it's 2.7 10 to 8 meters per second. And leave, oh boy, it leave 2.6 10 to minus 8 seconds when at rest relative to an observer. So You got it? So this is your proper time. How long do they live as viewed in the laboratory? Wait a second. Well, laboratory is supposed to be somebody observing that event. Okay, it's like you guys in the laboratory, SA115, measuring meson particles. So we want to find the t. So t is equal to t naught proper time divided by square root of 1 minus u over c squared. Okay, and then you just plug the numbers. So this time here should be longer than the proper time. Number 26. Number 26. Suppose a particle called kaon is created by cosmic radiation striking the atmosphere. It moves by u. Again, the speed is given. And leaves. Okay, now let's try to interpret this time before we put an index there. 1.24 10 to minus 8 seconds. So in leaves, went at rest relative to an observer. So this is the proper time again. How long does, so it's the same thing, right? So we apply the same equation, the same thing. It's just changing the numbers, but basically it's the same. Number 27. Number 27. Neutral pi meson is a particle that can be created by accelerator beams if one such particle leaves, again, t, leaves, as measured in the laboratory. Oh, so I think laboratory here is being used as a term to describe somebody outside. So it measures 1.4 10 to minus 16 seconds in the laboratory. So it is an observer at rest at Earth, and is measured these other times when at rest relative to an observer. What is its velocity with respect to the laboratory? Well, once you had set the equation this way, then you can find u. So it's a matter of doing math. Okay, that's number 27. Number 28, a neutron, number 28, leaves 900 when at rest relative to an observer. So t naught is 900 seconds. See, you have to learn to translate the information. How fast is a neutron moving relative to an observer who measure its lifespan? And then you have your time given. And then you plug your equation, and then you're good to go.
Can I come in? Okay.
I will continue in a second.